Hi everyone, this video is about the convergence of Taylor series. In this section, we will know that the Taylor series for function can converge to its generating function. We will estimating the remainder and the using of Taylor series, and there are some couple of examples. So, the Taylor series, the Taylor formula set is function f have a derivative of all order. Basically, it means that we keep taking the derivative in an open interval I containing a, we should know that it is the center. Then for each positive integer n and for all each x in the interval. So the following is true. We have the function f of x equal f evaluated at a plus this term, the first derivative evaluated at a, and so on. And for this one, we're not going to plus dot dot to infinitive. Instead, we stop it somewhere where this one we call it remainder or error. So the remainder of the order n is equal to n plus 1 derivative over n plus 1 factorial x minus a to the power n plus 1. So why is n plus 1? Because we stop here at the n. So this is the formulas of our remainder. So from that previous formulas, we can say it's like that. We can writing it like that. This is our function. It is equal the Taylor polynomials plus the remainder term. So in order to convert the Taylor series, the Taylor polynomial convert to the function that we want. So this term, the remainder term, have to be approach to 0. So if our remainder approach to 0, which means that it gets smaller as the end get bigger for all n belong to interval, then we can say that the Taylor series convert to f of x. Here's the proof. We have the series, the Taylor series. Here are the sum from k equals 0 to the infinity of f k derivative, yes, over the k factorial and x minus a to the power k is equal to the limit as n approach to infinity of this Taylor polynomial. And we know that Taylor polynomial is equal to f of x minus the remainder term, like the formula that I have shown you from the previous slide. So the limit of this function f is still the same because it is constant here over here, and then we got it the minus limit as n approach to infinity of our remainder term. So in order for f of x equal to Taylor series, the limit that as n approach to infinity have to approach to 0. So when it is equal to 0, we can say that f of x or Taylor series is equal to f of x here. And there are some common Taylor series that I want you to know because you will be able to use it later in order to practice some exercise. Here, just remember it. Yes, because this one we can know it from the previous section. 10.8 you can know about as well. So let's look at our first example. Show that the Taylor series generated by function f of x equal e to the x at x equals 0 convert to f of x for every value real value of x. So we know that the Taylor series of e to the x is equal 1 plus 1 x over 1 factorial plus x squared over 2 factorial and so on. And we stop right here at our remainder, and we know that the remainder is equal to this formula. this series. And yes, if we keep derivative the function e to the x, so we will still got e to the x is to x the same. So e to the x at evaluate at c, so it e to the c, and over n plus 1 and to the power n plus 1. So as the end approach to infinity, our reminder approach to zeros. It means that it gets smaller. So when it gets smaller, we can say that this series, it converts to e to the power x for every x. Okay, so let's move to the next slide about remainder estimating theorems. So if n plus 1 derivative, the absolute value n plus 1 derivative smaller or equal m, which is a positive constant m, for all t between x and a, then we can say that the absolute value of the remainder smaller or equal to m, again, absolute value of x minus a to the power n plus 1 over n plus 1 factorial. So if these inequality hold for every n and the other condition of Taylor's theorem are satisfied by f, then the series converges to f of x. So from the previous exercise, from exercise 1, we easy to know the derivative of e of x. But for some function, that's not easy, so we have to bound the remainder. So we have to find m. Okay, so let's take a look at this example. Show that Taylor series for sine x at x equals 0 converge to all x. So here we know that sine x is equal x minus x cubed over c factorial plus and so on. And we stop here at our remainder again. So we know that the derivative of since x has absolute value over 1, value less than or equal to 1. So we can say m is equal to 1. So here we can substitute that in our formula reminder. So n is equal to 2k plus 1. So when n plus 1 is equal to 2k plus 2, and since our center is 0, so a equals 0 and m equals 1, so we get this one. So as the k approach to infinity, it get larger, so the absolute value of our remainder is get smaller and smaller. You can see that this one gets larger, but this one, the factorial term is get larger than, so it approaches zeros. So we can say that the series converges to sine of x for every x. So using the Taylor series. So since every Taylor series is a power series, so the operation of adding, subtracting or multiplying Taylor series are all valid at the intersection of their interval of convergence. Let's look at the example. We have two examples over here. For A, we have 1 over 3 of 2x plus x cosine of x. So it is equal to 2x over 3 plus x over 3 multiplied to cosine x. We know the cosine, we know the Taylor series of cosine x is here. It's 1 minus 2 square over 2 factorial plus ... and so on. So let's just do it, evaluate it, and we get this answer. So get this series. So another one, it is similar to, so e to the x multiply cosine of x. So we know the Taylor series of these two functions for e to the x and for the cosine x. So we multiply it, this term to this one, and this term again to this one, we got minus, and so on, and then we got this answer. So this is about for my presentation. Thank you so much for your listening. Bye. Thank you.